Namaskaram. In this session, we will see another interpretation of double integration, that is mass of a lamina. The solution of last homework. Okay, in the introductory section of double integral, we have seen this infinite sum and we denote this infinite sum by like this double integral over r fxy dA. And what is delta ak? Delta ak is the area of the kth rectangle and xk star yk star is the arbitrary point from that kth rectangle, and the f of xk star yk star is the value of the function at that point. So this height from the surface, and this product is nothing, it is the volume. We can interpret this product as volume of this parallelepiped. Then we take the sum of all such parallelepipeds, that is approximately the volume of this shape, and that approximation is better when n tends to infinity, and we denote this infinite sum by double integral. Okay, so this is the one interpretation of this double integral. In this session we will see another interpretation of this infinite sum and this double integral. Okay, first I am going to define a term lamina. It's an ideal object. That means an idealized flat object that is thin enough to be viewed as a region in the two-dimensional plane. Okay, that means we can assume that its thickness is negligibly small. So very small. Okay, so we can view a lamina is a subset of our plane R2 or xy plane. Okay, there are two type of laminas or two type of materials. A lamina is called homogeneous if it is composition is uniform, otherwise it is called inhomogeneous. Okay, composition is uniform means throughout the same material. Throughout the same material means throughout same density. Okay, and inhomogeneous means otherwise it is called inhomogeneous. That means its density may differ depending on the point. Okay, for example, we consider a homogeneous lamina. That means it made by throughout the same type of material. Okay, so it is easy to find the density because density is throughout same, because it's a homogeneous lamina. So it made by homogeneous material. So here we assume that its total mass is m and total area of this lamina is a. Then we know that density equal to mass by area. So here in this case, in the case of homogeneous lamina, this density is throughout same. Whatever be the point, density is throughout same. Okay. So it is clear that mass by area, this is density. Density means mass per unit area. Okay, this is, so density is nothing, it is mass per unit area, and this density is throughout same for a homogeneous lamina. So it is clear that we can evaluate the mass of this material. Suppose density and area is known. Suppose the material is homogeneous and its density and area is known, then you can easily find the mass by taking the product density into area. Okay, this is the case for homogeneous material. Okay, so next we consider a inhomogeneous lamina. Inhomogeneous means the material is different. The composition of material is different, and the composition of material depends the points. Okay, suppose you have to find the density of the material at this particular point. Then how to find? So I am going to approximate this density using this formula delta my delta a. What is delta m? Delta m is the we consider a small aerial element containing the point. We consider a small aerial element containing the point, and its mass is delta m, and the area of this small element containing the point xy is delta a. Then you take the ratio. So this ratio is approximately the density at that point, and this ratio is better whenever this delta a is very small, right? So its area is very small, then this ratio is good approximation of density at the point. So the extreme case is limit delta a tending to 0. So we can define density function of a inhomogeneous lamina using this formula. Delta xy is equal to limit delta a tending to 0 delta m by delta a. Delta a means area of the small aerial element containing the point. Delta m is the corresponding mass of that small element. Okay. Conversely, suppose we have a small rectangular piece containing a point xy, and suppose the density at this point is known. Suppose this value is known. density function is known, then we can approximate the delta m. What is delta m? Delta m is the mass of this small rectangular piece containing xy. Then we can approximate delta m using this formula. Which formula? Delta of xy into delta a. Delta a is known. Here we assume that density function is also known. Then by the taking the product, that gives approximately the mass of this small point. Okay, we will use this technique. Okay, that means if density function is known, then we can approximate the mass of a small element using this formula. What is xy? Xy is an arbitrary point from that rectangular piece. That's all. Okay, we are going to evaluate the mass of this inhomogeneous lamina. So method is almost similar to our double integral, volume as a double integral. Imagine that the lamina to be subdivided into rectangular pieces using lines parallel to coordinate axis and excluding from the consideration any non-rectangular pieces at the boundary. That means we not considering these type of things. They are not rectangles. So we consider only the rectangles completely inside the lamina. That's all. Okay, we consider only rectangles completely inside the lamina. Suppose there are n such rectangles. So 1, 2, etc. This is our kth rectangle, etc. N. Suppose there are n such rectangles which are completely inside the lamina. Okay. And what is delta AK and delta MK? Delta AK stands for the area of the kth rectangle, and delta MK is the mass of the kth rectangle. Okay. Our aim is to evaluate the mass of entire body. Okay, so how to approximate mass of this lamina? Sum of all masses of these rectangles. That means sigma k equal to 1 to n. We assume that there are n such rectangles which are completely inside the lamina. Okay, into delta mk. Because delta m1, that is the mass of first lamina, delta m2 is the mass of second lamina, and then you take the sum. That's all. Okay, and here we assume that the density function is not. That means we know the density at a point xk star yk star. What is xk star yk star? It is an arbitrary point from the kth rectangle. Okay, so then we will use this formula. So how to approximate delta mk using the density function? Yes, we know that delta m is equal to delta xy into delta a. What is xy? Xy is an any point from that small element. Okay. Here we choose an arbitrary element is xk star yk star. So we can approximate this delta mk using the formula delta xk star yk star into delta a. Here instead of delta a, delta ak, the area of the kth rectangle. So next we are going to substitute this formula for delta mk. So this expression is like this. Okay, so m is approximated using this formula. Then we approximate delta mk using this formula. So ultimately we can approximate m using the formula sigma k is equal to 1 to n delta xk star yk star delta ak. And we know that this approximation is better whenever the number of rectangles is large or the size of the rectangles are very small. The size of the rectangles are very small mean automatically n tends to infinity. So this m is equal to, so m is the extreme case is n tends to infinity. So m is equal to limit n tends to infinity sigma k equal to 1 to n delta x k star y k star delta a k. Okay. Okay. Yes, this infinite sum is familiar. What is the integral notation of this infinite sum? Yes, we know that limit n tends to infinity sigma k equal to 1 to n f of x k star y k star delta a k is denoted by like this. So analogous to this, its integral representation is double integral over r delta xy dA. Delta xy is the density function of this inhomogeneous lamina. Okay, if you know the density function of the lamina, then you can easily find the mass of this lamina by using this double integral. Okay, so this is the another interpretation of our double integral. Mass of a lamina bounded by region R with the density function delta xy is double integral over R delta xy dA. Okay, consider a problem. A triangular lamina with the vertices 0, 0, 0, 1 and 1, 0 as density function delta xy is equal to xy. Find its total mass. Okay, first we have to identify the region of lamina. So it is clear that the triangular region bounded by these three vertices. That means this is our triangular lamina. So we have to find the equation of the straight line. Its equation is x plus y equal to 1. Okay, so this equation of the straight line is x plus y equal to 1. So next we have to find the mass of this lamina. We know that mass of this lamina is equal to double integral over r delta xy dA. Okay, so you can easily integrate this in rectangular coordinates. So I am going to consider a vertical strip. So what is the lower value of y? Yes, it is 0. And what is upper value of y? Y is equal to 1 minus x, right? So y is equal to 1 minus x. So 0 to 1 minus x. And to cover this region, x should varying from 0 to 1, right? Then only this strip cover this region. So x is varying from 0 to 1. And what is delta xy? Delta xy is xy. So the order of integration is dy dx. Clear? So you can easily integrate this double integral. So this becomes 0 to 1 x into y square by 2 0 to 1 minus x dx. So here 1 by 2 is common, you can take outside. So 1 by 2 into integral 0 to 1 x into y is 1 minus x. When y is 1 minus x, this becomes 1 minus x square. When y equal to 0, this time is 0. So this is the integral. Next you expand this 1 minus x square and multiply with x. So this integral become, so integral become like this, x minus 2x square plus x cube. Then you can integrate this with respect to x. So this is like this. Then next you substitute upper limit and lower. When x equal to 0, the time is 0. When you substitute 1, this become 1 by 2 minus 2 by 3 plus 1 by 4. And 1 by 2 is there. So upon simplification, this become 1 by 24. Okay, so the total mass of this triangular lamina is 1 by 24 units. Yes, 1 by 24. Okay, this is your homework. Thank you.